So here's something kind of wonderful to think about as you're lying there, getting comfortable, letting the day wind down. Every single time you've ever split a restaurant bill with friends, or figured out how many hours of sleep you'd get if you went to bed right now, or doubled a recipe because you've got extra people coming over for dinner. You were doing algebra. You just didn't call it that. Nobody sat you down and said, "Okay, now we're going to do some algebra." But that's exactly what was happening in your head. You were taking something you didn't know, working with things you did know, and figuring it out. That's it. That's the whole game. Everything else is just detail. And tonight, we're going to wander through those details together, slowly. There's no test at the end of this. There's nowhere you need to be. If you drift off somewhere along the way, that's perfectly fine. That's kind of the point. But if you stay with me, I think you'll find that algebra, the real story of it, is a lot more human and a lot more interesting than whatever you might remember from school. Because algebra wasn't invented in a classroom. It was invented by people who needed to solve real problems, people dividing up inheritances, people measuring fields after a flood, people trying to figure out how far a star had moved across the sky. It came from life. And it took thousands of years to become the thing we now learn in a semester. Let's start at the very beginning. And I mean the very beginning. Imagine you're living about 5,000 years ago, somewhere in the Fertile Crescent. That's the arc of land stretching from modern-day Iraq through Syria down into Egypt. This is where some of the earliest civilizations figured out how to farm, how to build cities, how to write things down. And once you start farming and building cities, you immediately run into problems that are, at their core, algebraic. You've harvested a certain amount of grain. You need to feed a certain number of people. You need to set aside seed for next year's planting. You need to pay a portion to the temple or the king. How much is left? How much does each family get? Now, they didn't write it the way we would. They didn't use X's and Y's. They didn't even have what we'd recognize as equations. But they were doing the same mental work. They were saying, in effect, I know the total. I know some of the parts. What's the missing piece? And that question, what's the missing piece, is the heartbeat of algebra. It's the question that drives everything. The Babylonians, who lived in what's now Iraq, were astonishingly good at this. We know because they wrote on clay tablets, and clay, unlike paper, survives for millennia. Archaeologists have dug up tens of thousands of these tablets, and a surprising number of them are mathematical. Some are basically homework. Seriously, they're practice problems for students at scribal schools, places where young people learn to read, write, and calculate. And some of these practice problems are unmistakably algebraic. Here's an example of the kind of problem a Babylonian student might have worked on roughly 4,000 years ago. It would be stated in words, something like, I have a rectangular field. The length exceeds the width by 7. The area is 60. What are the length and the width? Now, if you've taken any algebra at all, you might recognize that this is basically a system of equations. Length minus width equals 7. Length times width equals 60. But the Babylonian student wouldn't have written it that way. They had a procedure, a recipe almost, for solving this type of problem. They'd follow specific steps, manipulating the numbers in a particular order, and arrive at the answer. And their methods worked. They could solve problems that we would classify as quadratic equations, which is genuinely impressive. These are problems where the unknown quantity is squared, multiplied by itself, and they had reliable techniques for cracking them. Think about what that means. 4,000 years ago, before the alphabet as we know it existed, before iron tools, before coinage, Students in Mesopotamia were solving problems that many adults today would find challenging. They didn't have the notation we have. They didn't have the abstract framework. But they had the thinking. They had the problem-solving instinct. And here's what's really interesting about the Babylonian approach. It was entirely procedural. They'd say, take this number, multiply it by that, add this, take the square root, and there's your answer. It was like a cooking recipe. Do these steps in this order, and you'll get the right result. What they didn't do, and this matters, is explain why the steps worked. There was no proof, no general theory, just, here's the procedure. It works. Use it. And for practical purposes, that was enough. If you need to divide a field, you don't necessarily need to understand the deep theory behind the calculation. You just need the right answer. The Egyptians were doing similar things around the same time, maybe a little later. We know about their mathematics largely from a single remarkable document called the Rind Papyrus, named after a Scottish collector who bought it in the mid-1800s. It was written around 1650 BCE by a scribe named Ahmes, who noted that he was copying from an even older document. So this knowledge was already ancient when Ahmes wrote it down. The Rind Papyrus is essentially a math textbook. It contains about 84 problems with solutions, covering arithmetic, fractions, geometry, and some problems that are clearly algebraic in nature. One of the most famous types of problems in Egyptian mathematics is what they called aha problems. And no, that's not an exclamation of discovery. Aha was their word for the unknown quantity. It literally meant heap or quantity. So an aha problem would be something like a quantity, its whole, and its seventh, added together, make 19. What is the quantity? In modern notation, you'd write that as x plus x over 7 equals 19. Solve for x. But the Egyptian approach was different from both our modern method and the Babylonian method. They used something called the method of false position, which is a beautifully clever technique. Here's how it works. And stay with me, because this is actually really elegant. You don't know the answer, right? So you just guess. But you guess strategically. In that problem, a quantity plus a seventh of itself equals 19. You pick a number that makes the seventh part easy. So you guess 7. A seventh of 7 is 1. 7 plus 1 is 8. But you needed 19, not 8. So now you ask, what do I need to multiply 8 by to get 19? That's 19 divided by 8, which is 2 3/8. So you multiply your original guess, 7, by that same factor, 2 3/8, and you get your answer, 16 5/8. And if you check 16 5/8 plus a seventh of 16 5/8, you get 19. It works. Now why is this clever? Because you've turned a problem about an unknown into a problem about scaling. You took a convenient guess, saw how far off it was, and then scaled your guess to fit. You never had to solve for x in the way we think about it. You just had to be good at proportional reasoning, which the Egyptians absolutely were. They used this technique constantly, and it's actually still useful today in certain situations. Sometimes guessing and adjusting is faster than setting up a formal equation, especially for mental math. But here's the thing. Both the Babylonians and the Egyptians, as clever as they were, had a limitation. Everything was tied to specific problems. They could solve this field problem, that inheritance problem, this volume of grain problem. What they didn't have was a general language for talking about unknown quantities and the relationships between them. Each problem was its own little island. There wasn't a way to step back and say, all of these problems are really the same kind of problem. and here's a universal method for solving all of them. That leap, from specific problems to general methods, would take a very long time, and it would require a different way of thinking entirely. Now, you might be wondering where the Greeks fit into all of this, because we tend to think of the ancient Greeks as the great mathematicians. And they were, absolutely. But here's something funny. The Greeks were actually a bit suspicious of algebra, or at least of the kind of arithmetic-heavy problem-solving mathematics that the Babylonians and Egyptians practiced. The Greek mathematical tradition, especially the one that came down through Euclid and his contemporaries around 300 BCE, was deeply geometric. They thought about mathematics in terms of shapes, lengths, areas, and volumes. When a Greek mathematician wanted to think about what we'd call x squared, they didn't think of a number multiplied by itself. They thought of an actual square, a geometric shape with a certain side length. X squared was literally the area of a square. X cubed was the volume of a cube. This geometric approach was powerful in some ways. It gave Greek mathematics a visual, tangible quality, and it led to some extraordinary results. Euclid's Elements, which organized all of known geometry into a beautiful logical structure, is one of the most influential books ever written, but it also created a kind of ceiling. Because when you insist that everything be geometric, you run into trouble with problems that don't have an obvious geometric interpretation. What does it mean to raise something to the fourth power, geometrically? A four-dimensional shape? The Greeks didn't have a good answer for that, and so certain types of algebraic problems, ones that we'd find straightforward today, were awkward or even impossible to express in their framework. There was one Greek thinker, though, who pushed against this limitation, and he's worth spending a moment with. His name was Diophantus, and he lived in Alexandria, probably in the 3rd century CE, so quite late in the classical period. We don't know much about his life, which is kind of ironic because there's a famous riddle that supposedly describes it. The riddle says, "His boyhood lasted a sixth of his life. His beard grew after a 12th more. After a 7th more, he married. 5 years later, his son was born. The son lived half as long as the father, and the father died 4 years after the son." If you work through the math, and yes, this is an algebra problem about the man who helped shape algebra, you get that he lived to be 84. Whether that's true or legend, nobody knows. But the riddle itself is a perfect little example of what Diophantus cared about, using mathematical relationships to find unknown numbers. Diophantus wrote a work called the Arithmetica, and it was groundbreaking. He introduced a kind of shorthand notation for unknown quantities and their powers. It wasn't modern algebraic notation. It was still clunky by our standards, but it was a genuine step toward symbolic thinking. Instead of writing everything out in words, he had abbreviations, and he posed and solved problems that were purely numerical, not geometric. He was interested in finding numbers that satisfied certain conditions, and he developed techniques for doing so that were genuinely new. His work would later have an enormous influence, particularly on a mathematician working in 9th century Baghdad, a man whose name would literally become the word algebra. But that story, the story of al-Khwarizmi and the House of Wisdom, begins in a very different world, a world where scholarship was flourishing on a scale that's hard to overstate. We're talking about Baghdad in the early 9th century, during the reign of the Abbasid caliphs, and if you had to pick one city on earth at that moment where human knowledge was advancing the fastest, Baghdad would be it. Not Rome, not Constantinople, not Chang'an. Baghdad. And the reason is partly political, partly cultural, and partly just the right people being in the right place at the right time. The Caliph al-Ma'mun, who ruled from about 813 to 833 CE, was genuinely passionate about learning. Not just as a patron who threw money at scholars to make himself look good, though that was certainly part of it, but as someone who was personally curious, who wanted to understand the world. He established, or more accurately expanded, an institution called the Bait al-Hikmah, the House of Wisdom. Think of it as something between a library, a translation bureau, and a research institute. Scholars gathered there from across the Islamic world and beyond, Muslims, Christians, Jews, Zoroastrians, people from Persia, Central Asia, India, the Byzantine Empire. And one of the primary missions was to translate the great works of earlier civilizations into Arabic. Greek texts, Indian texts, Persian texts, Euclid's Elements, Ptolemy's Almagest, works of Aristotle, the astronomical tables of Indian mathematicians. All of it was being rendered into Arabic, studied, debated, and then built upon. And this is the world into which a man named Muhammad ibn Musa al-Khwarizmi stepped. We don't know his exact birth or death dates. Roughly 780 to 850 CE is the best guess. But we know he worked in Baghdad, probably at the House of Wisdom, and we know he wrote a book that changed everything. The book's full title, transliterated from Arabic, is something like Al-Kitab al-Mukhtasar fi Hisab al-Jabr wal-Muqabala, which translates roughly to the compendious book on calculation by completion and balancing. That word in the middle, al-Jabr, is where we get the word algebra, and the other word, al-Muqabala, refers to a different operation. Let's talk about what those words actually mean, because they're not just labels. They describe specific things you do to equations, and once you understand them, you understand the heart of what algebra is. Al-Jabr means something like restoration or completion. Imagine you have a situation where something has been subtracted from one side of a balance. Al-Jabr is the act of adding it back, restoring it, to make that side whole again. In modern terms, if you have something like x minus 5 equals 7, al-Jabr is the step where you add 5 to both sides to get rid of that subtraction. You're completing the left side. Al-Muqabala means balancing or comparing. It's the operation of canceling equal terms that appear on both sides. If you have x plus 3 equals 7 plus 3, al-Muqabala is the step where you remove the 3 from both sides because it's doing nothing. It's the same on each side, so you can simplify. Together, these two operations, completion and balancing, are the fundamental moves of algebra. Everything else builds on them. And al-Khwarizmi didn't just use them casually. He systematized them. He wrote them down as procedures that could be applied to whole categories of problems. Here's the thing that makes al-Khwarizmi's book so remarkable. He wasn't just solving individual problems the way the Babylonians did, where each clay tablet was basically a recipe for one specific situation. He was classifying equations into types and then providing a general method for solving each type. He identified 6 basic forms that equations could take, 6 canonical types, and for each one, he laid out a clear, step-by-step procedure. Now, he was working only with what we'd call linear and quadratic equations, and he required all the terms to be positive. He didn't have the concept of negative numbers as legitimate mathematical objects. So what we'd write as a single equation, like x squared minus 3x equals 10, he would rearrange using al-Jabr to make all terms positive, getting x squared equals 3x plus 10, and then recognize that as one of his 6 types. And he didn't use symbols. That's worth pausing on. Al-Khwarizmi wrote everything in words. Where we'd write x squared plus 10, x equals 39, he would write something like, a square and 10 roots equal 39. The unknown quantity was called a thing, shay in Arabic, and its square was called a mal, which means wealth or property. So his equations read almost like sentences, like little stories about things and their squares and how they relate to numbers. It's rhetorical algebra, algebra done entirely in prose. And yet, despite the lack of symbols, the thinking is genuinely algebraic. He's manipulating abstract quantities according to rules. He's solving for unknowns. He's proving that his methods work, using geometric arguments that would have made Euclid nod approvingly. Let me walk you through one of his solutions, because it's beautiful in its simplicity. Take the equation, a square and 10 roots equal 39. In our notation, that's x squared plus 10, x equals 39. Al-Khwarizmi's method goes like this. You take the number of roots, 10, and you halve it, getting 5. Then you square that half, getting 25. You add 25 to 39, getting 64. You take the square root of 64, which is 8. Then you subtract the 5 you set aside earlier, and you get 3. So x equals 3. And if you check, 3 squared is 9, plus 10 times 3 is 30. 9 plus 30 is 39. It works perfectly. Now, if you've ever taken an algebra class, you might recognize what he's doing. It's essentially the method we call completing the square, and he actually justified it geometrically. He drew a square with side length x, then added rectangles to represent the 10x term, and showed how you could rearrange everything into a larger square whose area you could calculate. It's a gorgeous fusion of geometric intuition and algebraic procedure, and it worked every time for every equation of that type. That's the power of it. It's general. It's not a trick for one problem. It's a method for an entire class of problems. Al-Khwarizmi's influence is hard to overstate. His book was translated into Latin in the 12th century, and it became the primary algebra textbook in European universities for centuries. The word algebra entered European languages directly from his title, and his own name, al-Khwarizmi, was Latinized into algoritmi, which eventually gave us the word algorithm, a step-by-step procedure for solving a problem. So the next time you hear someone talk about algorithms, whether it's about Google's search engine or the code running on your phone, know that the word traces back to a 9th century mathematician in Baghdad who wrote everything out in careful Arabic prose. But al-Khwarizmi wasn't working in isolation. He was drawing on Indian mathematics, which had made enormous advances in arithmetic, including the development of the decimal number system, the system we use today, with digits 0 through 9 and place value. The concept of 0 as a number, as something you could calculate with, came from Indian mathematicians, most notably Brahmagupta, who worked in the 7th century. Brahmagupta also did something al-Khwarizmi didn't. He worked with negative numbers and even laid out rules for arithmetic with them. Negative times negative is positive. Negative times positive is negative. These rules that you might remember from school? Brahmagupta wrote them down in 628 CE. And this is worth sitting with for a moment, because the story of algebra is also the story of expanding what counts as a number. The Babylonians worked with positive whole numbers and fractions. The Greeks were deeply uncomfortable with irrational numbers, numbers like the square root of 2 that can't be expressed as a fraction. The Indians embraced 0 and negative numbers. Each expansion opened up new territory for algebra because algebra is fundamentally about relationships between numbers, and the richer your number system, the more relationships you can express and explore. So, al-Khwarizmi gave us the framework, the idea that you could classify equations and solve them systematically. Indian mathematicians gave us the number system that made calculation practical, and over the next few centuries, mathematicians across the Islamic world pushed both of these traditions further. One figure who deserves special mention is Omar Khayyam. Yes, the same Omar Khayyam who's famous in the West for his poetry, for the Rubaiyat. He was born in 1048 in Nishapur, in what's now Iran, and he was a serious, brilliant mathematician. Khayyam tackled cubic equations, equations where the unknown is raised to the third power. Al-Khwarizmi had handled squares. Khayyam wanted cubes, and he found that he could solve certain cubic equations using the intersections of conic sections, parabolas, circles, hyperbolas. He'd set up two curves, find where they crossed, and the coordinates of that crossing point gave him the solution. It was geometric, it was ingenious, and it was also, in a sense, limited. Khayyam himself expressed frustration that he couldn't find purely numerical algebraic solutions to cubics. He wrote that perhaps future mathematicians would succeed where he hadn't. And he was right. They would, but it would take another 500 years, and the story of how it happened involves some of the most dramatic human conflict in the history of mathematics. It involves duels, betrayals, stolen formulas, and a mathematician who published someone else's secret on the pages of one of the most important mathematics books ever printed. So, let's talk about that. The setting is 16th century Italy, and the atmosphere is nothing like the quiet, scholarly world of the House of Wisdom. This is Renaissance Italy, competitive, theatrical, ego-driven. Mathematicians in this era didn't just publish papers and wait for peer review. They challenged each other to public contests. Imagine something like an intellectual boxing match. Two mathematicians would each submit a list of problems to the other, and they'd have a set period, sometimes 30 days, to solve them all. The winner got fame, prestige, sometimes a university position. The loser got humiliation. These weren't friendly exercises. Careers and livelihoods were genuinely at stake. And at the center of this world, around the 1530s, there's a man named Niccolò Fontana. You probably know him by his nickname, Tartaglia, which means the stammerer. He got that name because as a boy, during the French invasion of his hometown of Brescia in 1512, a soldier slashed his face with a saber. The wound cut through his jaw and palate, and it left him with a severe speech impediment for the rest of his life. He was about 12 years old. His father, a postal courier, had already been killed. His family was destitute, and yet this boy, largely self-taught, grew up to become one of the finest mathematicians in Italy. Here's the thing about Tartaglia. He discovered something extraordinary. He found a general method for solving cubic equations algebraically, not geometrically, the way Khayyam had done it with intersecting curves, but with an actual formula, a procedure that takes the coefficients of a cubic equation and gives you the answer through arithmetic and root extraction. This was the problem Khayyam had said he couldn't crack, and Tartaglia cracked it. Now, let's pause for a second and make sure we're comfortable with what a cubic equation actually looks like, because it matters for understanding why this was such a big deal. You know a linear equation, something like 3x plus 5 equals 20. One unknown, raised to the first power. Straightforward. A quadratic equation raises that unknown to the second power, x squared. Something like x squared minus 4 x plus 3 equals 0. Al-Khwarizmi's completing the square handles those beautifully. A cubic equation goes one step further. Now you've got x cubed in there, x raised to the third power, something like x cubed plus 6x equals 20. And solving these is dramatically harder. It's not just incrementally harder, the way going from addition to multiplication is a little harder. It's a qualitative leap. For nearly 4,000 years, from the Babylonians all the way through Khayyam, nobody had a purely algebraic solution for the general cubic. Tartaglia found one, but he kept it secret, and you can understand why. In a world where your mathematical knowledge is your competitive advantage, where public contests determine whether you get a professorship or starve, a secret formula for solving cubics is like a weapon. Tartaglia could challenge anyone, give them a list of 30 cubic equations, and solve all of theirs while they couldn't touch his. It was his ace in the hole. Enter Girolamo Cardano. Cardano was a physician, astrologer, gambler, mathematician, and one of the most colorful characters of the 16th century. He was born in Pavia in 1501, the illegitimate son of a lawyer who was friends with Leonardo da Vinci. Cardano was brilliant, and he knew it. He was also perpetually entangled in controversy. He'd later cast a horoscope of Jesus Christ, which got him imprisoned by the Inquisition. His personal life was marked by tragedy. One of his sons was eventually executed for murder, but in the 1530s, Cardano was a respected scholar in Milan, and he was working on a major book about algebra. He'd heard rumors that Tartaglia had solved the cubic, and he desperately wanted that solution. So in 1539, Cardano invited Tartaglia to Milan. He flattered him. He promised him an introduction to the Spanish governor of Milan, who might become a patron, and eventually, after much persuasion, Tartaglia agreed to share his method. But on one condition, Cardano had to swear an oath never to publish it. And Cardano swore. Tartaglia revealed his solution, apparently in the form of a cryptic poem, a mnemonic verse that encoded the algebraic steps, and Cardano, true to his word at least initially, kept it private. But here's where it gets complicated. Cardano didn't just sit on the formula. He studied it. He extended it. He and his brilliant young student, Lodovico Ferrari, began working through the implications, and Ferrari, who was genuinely a prodigy, Cardano had taken him in as a servant boy at age 14 and recognized his extraordinary talent. Ferrari managed to do something even more remarkable. He found a way to solve quintic equations. That's equations with x to the fourth power. And here's the kicker. Ferrari's method for quintics actually depended on being able to solve cubics first. You reduce the quintic to a cubic, solve that, and use the result to crack the quintic. So the cubic solution wasn't just a standalone achievement, it was a key that unlocked the next level. Now Cardano had a problem. He had this incredible body of work, the cubic solution, Ferrari's quintic solution, a whole systematic treatment of equations. And he couldn't publish any of it because of his oath to Tartaglia. But then something happened. Cardano traveled to Bologna and got access to the old notebooks of a mathematician named Scipione del Ferro. And in those notebooks, he discovered that Del Ferro had actually solved the cubic before Tartaglia, probably around 1515, maybe even earlier. Del Ferro had been a professor at the University of Bologna, and he'd found the solution, but, like Tartaglia after him, kept it secret. He shared it only with a few students, including a man named Antonio Fior. And it was actually Fior who had challenged Tartaglia to a public contest in 1535, armed with Del Ferro's method for one type of cubic, which pushed Tartaglia to discover the general solution on his own. So Cardano reasoned, and this is where you can debate the ethics, that since Del Ferro had discovered it first, and since his oath to Tartaglia was about Tartaglia's secret, and since the secret turned out not to be exclusively Tartaglia's after all, he was free to publish. Whether you find that argument convincing probably says something about you. Tartaglia certainly didn't find it convincing. He was furious. In 1545, Cardano published his masterwork, the Ars Magna, the Great Art, and it is, genuinely, one of the landmark books in the history of mathematics. In it, he presents the solution to the cubic, which he credits to both Del Ferro and Tartaglia, and Ferrari's solution to the quartic. He's actually quite generous with credit in the text itself, but Tartaglia didn't care about credit in a footnote. He felt betrayed. He'd shared his deepest secret under oath, and now it was printed for anyone to read. What followed was a bitter public feud. Tartaglia published attacks on Cardano. Ferrari, loyal to his mentor, challenged Tartaglia to a public debate. And in August 1548, in a church garden in Milan, they faced off. The accounts suggest Ferrari got the better of the exchange. Tartaglia actually left before it was finished. After that, Tartaglia's reputation suffered, and he spent his remaining years in relative obscurity. He died in 1557, still bitter about what he saw as Cardano's betrayal. Now, let's step back from the human drama for a moment and think about what was actually achieved here, because it's profound. For the first time in history, mathematicians had general algebraic solutions for cubic and quartic equations. Think about what that means in the arc we've been following. The Babylonians could handle linear and some quadratic problems. Al-Khwarizmi systematized quadratics. And now, in one explosive decade in 16th century Italy, cubics and quartics fell. The frontier of algebra lurched forward by 2 entire degrees, and the formula itself, what we now call Cardano's formula, though Tartaglia and Del Ferro deserve at least equal credit, is worth savoring for a moment. For a simplified cubic like x cubed plus px equals q, the solution involves taking the cube root of a quantity that includes q over 2, plus the square root of a combination of p and q, then adding the cube root of another similar expression. It's not simple the way the quadratic formula is relatively simple. It's nested, roots inside roots. But it works. You plug in your coefficients, grind through the arithmetic, and out comes x. And here's something beautiful and strange that emerged from this formula, something that would have deep consequences. Sometimes, when you applied Cardano's formula to a cubic equation that you knew had perfectly real, ordinary solutions, numbers you could point to on a number line, the intermediate steps of the calculation required you to take the square root of a negative number, the square root of -1, for instance. Now, there's no real number that, when multiplied by itself, gives you -1. 2 times 2 is 4. -2 times -2 is also 4, because a negative times a negative is positive. So the square root of -1 doesn't exist, at least not among the numbers anyone recognized at the time. But the formula demanded it. You'd get these impossible square roots appearing in the middle of the calculation, and then, almost magically, they'd cancel each other out at the end, leaving you with a perfectly real answer. It was like walking through a wall to get to the other side of a room. The wall shouldn't be passable, but somehow you passed through it and ended up exactly where you needed to be. This was deeply unsettling. Cardano himself called these quantities sophistic and, as subtle as they are, useless. But they weren't useless at all. They were the first glimpse of what we now call imaginary numbers and complex numbers, an entirely new kind of number that would eventually become essential to everything from electrical engineering to quantum mechanics. And it was algebra, specifically the quest to solve cubic equations, that forced mathematicians to confront them. This is that pattern again. Algebra expanding the boundaries of what counts as a number. First zero, then negatives, then irrationals, and now these strange square roots of negative numbers that shouldn't exist, but somehow do. And yet they kept showing up, like uninvited guests who turn out to be the most interesting people at the party. So let's stay with that for a moment, because the story of how these impossible numbers went from being an embarrassment to being one of the most powerful tools in all of mathematics, that story is worth telling slowly. It took centuries, and it's a beautiful example of something that happens over and over in the history of algebra. Mathematicians stumble onto something that seems absurd, maybe even meaningless, and they try to ignore it or explain it away. And then eventually, reluctantly, they accept it. And it turns out to open up an entire world they couldn't see before. The first person to really take these strange quantities seriously, to actually work with them deliberately, rather than just watching them appear and disappear inside Cardano's formula, was a man named Raphael Bombelli. He was an Italian engineer, born in Bologna around 1526, so just a generation after Cardano. Bombelli wasn't a university professor. He was a practical man, a hydraulic engineer who worked on draining marshes and building bridges. But he was also deeply interested in algebra, and he read Cardano's Ars Magna carefully, and he noticed the same thing we just talked about, that the cubic formula sometimes produced these expressions involving square roots of negative numbers, even when the equation had perfectly good real solutions. Most mathematicians at the time just threw up their hands at this. They called it the irreducible case, casus irreducibilis, and treated it as a kind of defect in the formula. But Bombelli did something different. He said, okay, let's just accept these things for now. Let's treat the square root of -1 as if it were a legitimate number, give it some rules for how it behaves, and see if we can make the arithmetic work out. He called it più di meno, plus of minus, which was his way of saying the square root of -1, and meno di meno for its negative. And then he just did arithmetic with them. He added them, multiplied them, followed the rules carefully, and showed that when you work through the cubic formula, using these impossible quantities, everything comes out right at the end. The imaginary parts really do cancel, and you get the real solutions you expected. This was a huge conceptual leap, even though it might not sound like one. Because what Bombelli was really saying was, these numbers may not make sense to us yet, but they follow consistent rules, and when we use those rules, we get correct answers. So maybe the problem isn't with the numbers. Maybe the problem is with our intuition about what a number should be. That's a remarkably modern attitude for someone writing in the 1570s. And here's the thing. Bombelli published this work in a book called simply L'Algebra in 1572. It's one of those books that was ahead of its time. People respected it, but they didn't fully absorb what it was saying. The mathematical world wasn't quite ready to embrace imaginary numbers as real things. It would take another 200 years before that happened in earnest. But let's not jump ahead too fast. Let's linger in this period, because something else was happening in the late 1500s and early 1600s that would change algebra just as profoundly as imaginary numbers, and in some ways even more so. And that's the invention of modern algebraic notation, the symbols, the letters, the plus signs, the equal signs, the way we actually write equations today. Because remember, up to this point, almost everything in algebra was still written out in words. Al-Khwarizmi wrote everything as sentences. Cardano's Ars Magna used abbreviations here and there, but it was still mostly rhetorical. Imagine trying to do serious algebraic manipulation when every equation is a paragraph. It's like trying to do long division using Roman numerals, technically possible, but agonizingly slow and error-prone. The shift to symbolic algebra didn't happen all at once. It was gradual, with different mathematicians contributing different pieces. But there are a few key figures worth knowing about. One is François Viète, a French lawyer and mathematician who worked in the late 1500s. Viète had a fascinating life. He served as a codebreaker for King Henry IV of France, deciphering encrypted Spanish diplomatic correspondence during the Wars of Religion. The Spanish were so convinced their codes were unbreakable that when they found out the French were reading their messages, they complained to the Pope that France must be using sorcery. That's a real story, by the way. Viète was just very, very good at pattern recognition, and that same talent for seeing patterns made him a brilliant algebraist. In 1591, he published a work called In Artem Analyticam Isagoge, an introduction to the analytic art, in which he did something genuinely revolutionary. He used letters to represent not just unknowns, but also known quantities. Before Viète, if you had a general rule about equations, you had to state it in words or show it through specific numerical examples and hope the reader understood the pattern. Viète said, "Let's use vowels for unknowns and consonants for known constants." So instead of saying a number whose square, added to 5 times the number, equals 24, you could write something much more compact and general. You could talk about the structure of the equation itself, independent of any particular numbers. This might seem like a small thing, but think about what it means. Once you have symbols for both unknowns and knowns, you can write down a general equation. Not just a specific problem, but an entire family of problems at once. You can manipulate the symbols, rearrange them, discover relationships between them, prove things about all equations of a certain type. It's the difference between arithmetic and algebra in the deepest sense. Arithmetic says, what's 3 plus 5? Algebra says, what can we say about a plus b, no matter what a and b are? Viète's notation made that kind of thinking not just possible, but natural. Now, Viète's specific notation didn't survive. The system we actually use today, x for unknowns, a, b, c for constants, superscripts for exponents, the whole apparatus that comes largely from René Descartes, writing about 40 years later. Descartes published his famous Discourse on the Method in 1637, and one of its appendices was called La Géométrie, and in it he laid out a notation for algebra that is remarkably close to what you'd see in any textbook today. He used the last letters of the alphabet, X, Y, Z, for unknowns, and the first letters, A, B, C, for known quantities. He wrote x squared as x with a small 2 above it. He used the same symbols for addition and subtraction that we use now. And this is where something magical happens. Once you have good notation, algebra becomes almost visual. You can see the structure of an equation. You can see what to do next, what to add to both sides, what to factor out, where to substitute. The notation does some of your thinking for you. It's like the difference between trying to navigate a city by verbal directions versus having a map. The map doesn't just show you where things are. It reveals relationships, shortcuts, patterns you'd never notice from the ground. Descartes did something else in La Géométrie that was equally profound, and this connects back to those ancient Greeks we talked about earlier. Remember how the Greeks did their algebra geometrically? Every equation was a relationship between lengths and areas and volumes. Descartes essentially unified algebra and geometry. He showed that you could take any geometric curve and describe it with an algebraic equation, and conversely, you could take any equation and visualize it as a curve. This is what we now call analytic geometry or coordinate geometry, the idea of plotting equations on a grid with an x-axis and a y-axis. Every time you've seen a graph of a line or a parabola or a circle described by an equation, you're looking at Descartes' invention. And think about what this means for our story. The Greeks had kept algebra trapped inside geometry. Everything had to be a length or an area. The Islamic algebraists and the Italian algebraists had been slowly freeing algebra from geometry, making it more abstract, more symbolic. And now Descartes comes along and reunites them, but on algebra's terms. Geometry becomes a tool for visualizing algebraic relationships rather than the other way around. The power dynamic has flipped. Algebra is now the deeper language, and geometry is one of its applications. This is happening in the early to mid-1600s, and it's worth pausing to appreciate just how much has changed. In the space of about a century, from Cardano's Ars Magna in 1545 to Descartes' La Géométrie in 1637. Algebra has gone from a collection of verbal recipes for solving specific types of equations to a symbolic, general, powerful language for describing mathematical relationships of all kinds. It has its own notation, its own rules of manipulation, its own way of thinking. It's becoming the backbone of mathematics itself. And here's where things start to accelerate, because this new symbolic algebra is about to collide with another revolution happening at exactly the same time. The scientific revolution. Galileo, Kepler, and eventually Newton and Leibniz are all working in this same period, trying to understand the physical world, how planets move, how objects fall, how light bends, and they need a language to express the patterns they're finding in nature. Algebra gives them that language. When Newton sits down in the 1660s to figure out the laws of motion and gravitation, he's not doing it in words. He's not drawing geometric diagrams the way Euclid would have. He's writing equations. Force equals mass times acceleration. The gravitational force between two objects is proportional to the product of their masses, divided by the square of the distance between them. These are algebraic statements, relationships between quantities expressed in symbols, ready to be manipulated, combined, solved. Without the symbolic algebra that Viette and Descartes and others had developed, Newton's physics would have been nearly impossible to formulate, let alone to use. And Newton, along with Leibniz, invented calculus, which you can think of as algebra's most powerful extension, a way of handling quantities that are continuously changing. But calculus is built on algebra. Every derivative, every integral, every differential equation. It's all algebraic manipulation at its core, just applied to a new kind of problem. So when we say algebra is the language of science, we really mean it. It's not a metaphor. It's literally the notation and the rules of manipulation that scientists use to express and discover the laws of nature. But let's come back from that big picture for a moment, because there's a specific thread I want to follow. A problem that had been nagging at mathematicians ever since Cardano and Ferrari's time. And that was about to produce one of the most surprising and consequential results in the entire history of mathematics. Remember, Cardano's formula solved the cubic, degree 3. Ferrari's method solved the quartic, degree 4. The natural question, the obvious next step, was, what about the quintic, the 5th degree equation? Surely someone, somewhere, could find a formula. Some combination of addition, subtraction, multiplication, division, and root extraction that would solve any 5th degree polynomial equation. People tried. They tried for over 200 years. Some of the greatest mathematicians in the world took a crack at it. Euler, Lagrange, Bezout. They made partial progress, developed clever techniques, but the general quintic formula remained stubbornly out of reach. And slowly, a strange suspicion began to form. What if it wasn't just hard to find? What if it didn't exist? What if there was no such formula? Not because nobody was clever enough to discover it, but because the universe itself wouldn't allow it. That the very structure of mathematics made it impossible? And here's the thing. That suspicion turned out to be correct. But proving it, actually demonstrating beyond any doubt that no quintic formula could ever exist, required a completely new way of thinking about algebra. And the people who figured it out were, in many ways, the most tragic and romantic figures in the entire history of mathematics. Let's start with the first one. His name was Niels Henrik Abel, and he was Norwegian, born in 1802 in a small town called Finnøy. His father was a pastor, and the family was poor, not comfortably modest, but genuinely struggling. Abel showed extraordinary mathematical talent from a young age, which was recognized by one of his teachers at the cathedral school in Christiania. That's modern-day Oslo. This teacher, a man named Bernt Michael Holmboe, spotted something remarkable in the teenage Abel and began lending him books, guiding him through the works of Euler and Lagrange and the other great mathematicians of the previous century. And Abel devoured them. He didn't just read them. He engaged with them, pushed past them, started asking questions that went beyond what those masters had answered. By the time Abel was about 19, he believed he had proven that the general quintic equation could not be solved by radicals. Now, solved by radicals is a specific technical phrase, and it's worth pausing on for a moment. When we say solved by radicals, we mean, can you write down a formula that gives you the answer using only the basic arithmetic operations, adding, subtracting, multiplying, dividing, plus taking roots, square roots, cube roots, fifth roots, whatever. That's what Cardano's formula does for cubics. It's a big, messy expression, but everything in it is built from those basic operations. So the question about the quintic was, is there any formula, no matter how complicated, that uses only those operations and works for every possible fifth-degree equation? Abel said no, there isn't. And he wrote up a proof. Now, his first attempt, which he published himself as a pamphlet in 1824, was compressed. He was trying to save money on printing costs, so he squeezed everything down to just 6 pages. 6 pages to prove something that the greatest minds in mathematics had been chasing for 2 centuries. It was dense, it was hard to follow, and initially almost nobody read it. He sent copies to leading mathematicians, including Gauss, Carl Friedrich Gauss, arguably the most famous mathematician alive at the time. Gauss apparently glanced at it and set it aside, didn't engage with it, which, if you think about it, is heartbreaking. Here's this young, impoverished Norwegian genius sending his life's work to the one person who might understand it, and it just lands on a pile. Abel eventually published a more detailed version of his proof in 1826 in a respected German journal, Krell's Journal, one of the first major journals dedicated to pure mathematics, founded by August Leopold Krell, who became a champion of Abel's work. And this time, people did start to pay attention. The proof, once mathematicians worked through it carefully, was correct. Abel had shown, rigorously, that there is no general algebraic formula for the roots of a polynomial equation of degree 5 or higher. Think about what that means. For thousands of years, algebra had been about solving equations, finding the unknown. And here was a result that said, for this entire infinite class of equations, the thing you're looking for doesn't exist. It's not that you haven't found it yet. It's that it's provably, permanently, forever impossible. There is no combination of additions, subtractions, multiplications, divisions, and root extractions that will give you the solutions to every quintic. The road just ends. And Abel proved this at 22. But here's the sad part. Abel never received the recognition he deserved during his lifetime. He traveled to Berlin and Paris, hoping to connect with the mathematical establishment. But he was shy, he was poor, and the gatekeepers of European mathematics were slow to embrace an unknown Norwegian. He submitted a major paper to the French Academy of Sciences, and it was essentially lost, misplaced by Cauchy, one of the referees, and not published until years after Abel's death. Abel returned to Norway without a permanent university position, took on tutoring work to survive, and contracted tuberculosis. He died on April 6, 1829, at the age of 26. 2 days after his death, a letter arrived offering him a professorship in Berlin. It's one of those stories that just stays with you. The timing is almost cruel, but Abel's result, what we now call the Abel-Ruffini theorem, since an Italian mathematician named Paolo Ruffini had published an earlier, incomplete attempt at the same proof around 1799, that result is permanent. It changed what mathematics was about. It wasn't just a negative result, a dead end. It was a doorway into a completely new way of thinking. Because once you know that you can't solve every quintic, the next question becomes, why not? What is it about fifth-degree equations that makes them fundamentally different from fourth-degree equations? What changes between degree 4 and degree 5? And that question, the why, was answered by someone even younger and even more tragic than Abel. His name was Évariste Galois, and his story is one of the most extraordinary in all of mathematics. Galois was French, born in 1811 in Bourg-la-Reine, a small town just south of Paris. His father was the mayor of the town, a witty and liberal-minded man. Galois was educated at the Lycée Louis-le-Grand in Paris, one of the most prestigious schools in France. But he was a difficult student, brilliant and impatient, bored by the standard curriculum, and increasingly absorbed in mathematics to the exclusion of everything else. He read Legendre's geometry textbook, meant to be studied over 2 years, in 2 days. He moved on to Lagrange's original research papers, which most professional mathematicians found challenging. He was 15, maybe 16. Galois applied twice to the École Polytechnique, the most elite scientific institution in France, and was rejected both times. The stories about his entrance exams have become legendary. Some accounts say he threw an eraser at an examiner who asked a question he found stupid. Whether that specific detail is true or embellished, the pattern is clear. Galois was not someone who played well with institutional authority. He ended up at the École Normale, a lesser institution, and continued developing his mathematical ideas largely on his own. And those ideas were extraordinary. What Galois did, in a series of papers written between roughly 1829 and 1832, was to connect the solvability of a polynomial equation to the structure of a certain group of permutations associated with its roots. Now, I need to unpack that a little, because this is genuinely one of the deepest ideas in all of mathematics, and it's worth taking slowly. Think about it this way. Say you have a polynomial equation, some fifth-degree equation with specific coefficients. That equation has 5 roots, 5 solutions, Even if you can't write them down with a nice formula, they exist as numbers, out there in the mathematical landscape. Now, Galois asked, what happens if you shuffle those roots around? What if you swap root number 1 with root number 3, or rearrange all 5 of them in some new order? Some of those rearrangements will preserve all the algebraic relationships among the roots, and some won't. The collection of rearrangements that do preserve those relationships forms what Galois called a group. And here's the key insight, the really beautiful part. Galois showed that whether or not an equation can be solved by radicals depends entirely on the structure of this group. Specifically, the equation is solvable by radicals if and only if its group has a certain property, a property we now call being solvable, which is a technical term meaning the group can be broken down into a chain of simpler pieces in a very specific way. For quadratics, cubics, and quartics, the associated groups always have this property. They're always solvable. That's why formulas exist for those equations. But for the general quintic, the associated group is what we call the symmetric group on 5 elements, all possible rearrangements of 5 things, and this group is not solvable. It can't be broken down in the required way. And that's why no formula exists. This is stunning. Galois had found the deep structural reason behind Abel's impossibility result. It wasn't just that nobody had been clever enough. It was that the symmetry structure of 5th-degree equations is fundamentally more complex than that of lower-degree equations. There's a kind of irreducible complexity that kicks in at degree 5, and it's precisely this complexity that blocks any formula built from radicals. And Galois did all of this by the age of 20. But his life was spiraling. His father committed suicide in 1829 after a political dispute. Galois became involved in radical Republican politics during one of the most turbulent periods in French history, the July Revolution of 1830 and its aftermath. He was arrested twice, once for threatening the king's life at a banquet. He allegedly raised a glass with a dagger in hand. Again, the exact details are disputed, and spent several months in prison. His mathematical papers were submitted to the French Academy of Sciences multiple times, and were lost, rejected, or ignored. Cauchy, the same Cauchy who misplaced Abel's paper, was involved again. Fourier, another academician who received one of Galois' submissions, died before reading it. It's as if the institutional machinery of mathematics was actively conspiring against this young man, though of course it was just bureaucratic indifference and bad luck. On May 30th, 1832, Galois fought a duel. The exact circumstances are murky. It may have been over a romantic entanglement. It may have had political dimensions. The full story has been debated by historians for nearly 2 centuries. What we know is that the night before the duel, Galois stayed up writing. He wrote letters to friends, and he wrote mathematics, frantically scribbling notes in the margins of his papers, trying to get his ideas down before morning. In the margins, he wrote things like, "I have not time," and "There is something to complete here." He was 20 years old, and he seemed to know he was going to die. He was shot in the abdomen during the duel the next morning and died the following day, on May 31st, 1832. He was buried in a common grave. It took more than a decade for his work to be properly published. In 1846, Joseph Liouville finally edited and published Galois' manuscripts, and the mathematical world began to understand what it had lost. What Galois had created, what we now call Galois theory, became one of the cornerstones of modern algebra. It's not an exaggeration to say that it transformed the entire field. Before Galois, algebra was primarily about solving equations. After Galois, algebra became the study of structure, the study of groups, symmetries, abstract patterns. The focus shifted from find the answer to understand why the answer does or doesn't exist, and what deeper architecture governs the possibilities. And that shift, from computation to structure, is arguably the most important conceptual revolution in the history of algebra. It's what separates ancient algebra from modern algebra. And it happened because a brilliant, angry, politically radical 20-year-old asked not just, can we solve this equation, but what would it mean, structurally, for an equation to be solvable? Now you might be wondering, if you can't solve a general quintic with a formula, does that mean fifth-degree equations are just unsolvable? Not exactly. It means you can't write down a universal formula using only the basic operations plus roots, but specific quintic equations can sometimes be solved. It depends on the particular coefficients, and therefore on the particular Galois group associated with that equation. And there are other methods, using more exotic mathematical tools like elliptic functions, that can express the roots of any quintic. A mathematician named Charles Hermite showed this in 1858, using something called elliptic modular functions to solve the general quintic. So, the roots exist, and they can be expressed, just not with the classical toolkit of radicals. But the deeper legacy of Galois' work isn't really about quintics at all. It's about the idea that you can study mathematical objects by studying their symmetries, that you can classify equations and shapes and physical systems by understanding the groups of transformations that leave them unchanged. This idea, that symmetry is the key to understanding structure, rippled outward from Galois theory into virtually every branch of mathematics and physics. When physicists today talk about symmetry groups governing the fundamental forces of nature, when chemists use group theory to understand molecular vibrations, when cryptographers build encryption systems on the algebraic structure of elliptic curves, all of that traces back, in a very real sense, to what Galois scribbled in the margins of his papers the night before he died. So let's sit with that for a moment. We've come a long way from the Babylonian scribes pressing wedge-shaped marks into clay tablets to solve problems about fields and canals. Thousands of years of human effort, from the rhetorical puzzles of al-Khwarizmi to the symbolic machinery of Descartes, from Cardano's reluctant publication of Stolen Secrets to Galois' desperate midnight writing. All of it building, layer upon layer, toward a deeper understanding of what equations are and what they can tell us. And now, with Galois theory in hand, algebra was no longer just a tool for solving problems. It was becoming something more abstract, more powerful, and more strange. Because once mathematicians started thinking about groups and symmetries as objects of study in their own right, they began to realize that these abstract structures showed up everywhere, in geometry, in number theory, in the study of transformations themselves. And that's really where algebra starts to grow up, if you can think of it that way. It stops being about finding the value of X and starts being about understanding entire systems of relationships all at once. So let's talk about what happened after Galois. Because his ideas didn't just sit there in Liouville's 1846 publication gathering dust. They caught fire, slowly at first, then with an intensity that reshaped the entire landscape of mathematics. And the person who probably did the most to fan those early flames was a quiet, methodical Englishman named Arthur Cayley. Cayley is one of those figures who doesn't get the dramatic biographies. He wasn't a tragic genius dying young. He wasn't fighting duels or stealing formulas. He was a lawyer, actually, a very successful one, who did mathematics on the side for 14 years before finally getting a professorship at Cambridge in 1863. But during those 14 years of practicing law by day and doing math by night, Cayley was astonishingly productive. He published hundreds of papers, and one of the things he kept returning to was this idea of groups. In 1854, Cayley wrote a paper that did something deceptively simple but profoundly important. He defined a group in purely abstract terms, not as a group of permutations of roots, the way Galois had used them, not as symmetries of a specific geometric object, just a set of elements with an operation that combines any two of them, following certain rules. The operation has to be associative, meaning if you combine three things, it doesn't matter which pair you combine first. There has to be an identity element, something that, when you combine it with anything else, leaves that thing unchanged. And every element has to have an inverse, something you can combine it with to get back to the identity. That's it. Those are the rules. And if you're lying there thinking, wait, that sounds like it could describe a lot of things, you're exactly right. That's the whole point. Cayley realized that the same abstract structure shows up in wildly different contexts. The integers under addition form a group. 0 is the identity, and every number has a negative that brings you back to 0. The rotations of a square form a group. The permutations of a set of objects form a group. Even the hours on a clock form a group, if you think of addition modulo 12. 1 o'clock plus 11 o'clock brings you back to 12, which is really 0. It's the same abstract pattern wearing different costumes. And here's what's really clever about thinking this way. Once you prove something about the abstract group, some theorem about how groups behave in general, that theorem automatically applies to every single concrete example. You prove it once, and it works for number systems, for symmetries of crystals, for permutations, for clock arithmetic, for all of them simultaneously. That's an extraordinary amount of leverage from a very small set of axioms. Now, Cayley wasn't working alone in this. Around the same time, other mathematicians were discovering group-like structures in their own corners of mathematics. There was a growing sense that algebra wasn't really about numbers and equations at all. It was about operations and structures. And this realization led to an explosion of new algebraic objects in the second half of the 19th century. Think about it this way. For thousands of years, algebra had basically one job: solve equations involving numbers, find the unknown quantity. But now, mathematicians were asking a different kind of question. They were saying, what if we forget about numbers entirely and just study the rules of combination? What kinds of systems can we build? What happens if we change the rules slightly? And when you start pulling on that thread, you get some fascinating things. You get rings, which are like groups, but with two operations, addition and multiplication, that interact in specific ways. The integers are a ring. Polynomials form a ring. You get fields, which are rings where you can also divide. The rational numbers are a field. The real numbers are a field. You get vector spaces, where you can add things and scale them. Each of these structures captures a different flavor of algebraic behavior, a different set of rules that show up again and again in different parts of mathematics. And the person who really started to systematize all of this, who saw the big picture of how these abstract structures related to each other, was Emmy Noether. And honestly, if you only remember one name from this part of the story, it should probably be hers. Emmy Noether was born in Erlangen, Germany, in 1882. Her father, Max Noether, was a well-known mathematician, so she grew up surrounded by mathematical ideas. But here's the thing. When she wanted to study mathematics at the University of Erlangen, she wasn't allowed to enroll. Not because she wasn't qualified, because she was a woman. This was Germany at the turn of the 20th century, and women were officially barred from matriculating at most universities. She could audit classes with individual professors' permission, but she couldn't be a regular student. She did it anyway. She sat in on lectures. She learned the material, and in 1907 she earned her doctorate, summa cum laude, working under Paul Gordon on a problem in the theory of invariance. Now, invariant theory is one of those areas that connects directly to the story we've been telling. An invariant is something that doesn't change when you apply a transformation. Think about it. If you rotate a circle, it still looks like a circle. The radius is invariant under rotation. If you have an algebraic expression and you permute the variables in certain ways, some properties of that expression might stay the same. Those are invariants. And studying invariance is really just another way of studying symmetry, which is really just another way of studying groups. It all connects. After her doctorate, Noether couldn't get a proper academic position. She worked unpaid at Erlangen for years, helping her father, doing research, publishing papers. In 1915, David Hilbert and Felix Klein, two of the most powerful mathematicians in the world, both at the University of Göttingen, recognized her brilliance and tried to get her a faculty position there. The philosophy department objected. One faculty member reportedly asked, "What will our soldiers think when they return to the university and find that they are required to learn at the feet of a woman?" Hilbert's response has become legendary. "I do not see that the sex of the candidate is an argument against her admission. After all, we are a university, not a bathhouse." She didn't get the position, not right away. She lectured for years under Hilbert's name. Courses would be officially listed as his, but she was the one teaching them. She finally got a proper appointment in 1919, after the political changes following the First World War loosened some of the old restrictions. And even then, for years, she wasn't paid a real salary. But none of that stopped her from doing some of the most important mathematics of the 20th century. In 1921, she published a paper called Idealtheorie in Ringbereichen, Theory of Ideals in Ring Domains. And it changed everything. What Noether did was take all these algebraic structures that people had been discovering piecemeal, groups, rings, fields, modules, ideals, and she showed how to study them systematically using a small number of powerful, abstract principles. She focused on the relationships between structures rather than on specific computations. She asked questions like, when can you break a structure down into simpler pieces? What are the fundamental building blocks? How do different structures map onto each other? This approach, studying algebra through the lens of abstract structures and the maps between them, became known as modern algebra, or abstract algebra. And it's not an exaggeration to say that Noether essentially created the field as we know it. The textbook that spread her ideas to a whole generation was Moderne Algebra by van der Waerden, published in 1930 and 1931, and it was based largely on lectures by Noether and her colleague Emil Artin. If you take an abstract algebra course at any university in the world today, you are learning a subject that Noether shaped. Now here's something beautiful about all this, and I want you to just let it wash over you. Remember how we started this whole journey? with Babylonian scribes solving specific problems about specific fields with specific areas. They'd say, I have a rectangle. The length exceeds the width by 7. The area is 60. Find the dimensions. And they had recipes, step-by-step procedures for getting the answer. Then, al-Khwarizmi organized those recipes into general types. Then Viet and Descartes gave us symbols so we could write those types down compactly. Then people like Abel and Galois asked not just, how do we solve this equation, but can it be solved, and why or why not? And now, with Noether, mathematics has reached a level of abstraction where you're not even talking about equations anymore. You're talking about the structures that equations live inside. You're studying the architecture of mathematical systems themselves. Each generation climbed one rung higher on the ladder of abstraction. And at every step, the new level of abstraction turned out to be not less useful, but more useful, because it revealed connections that were invisible from below. And Noether herself proved one of the most stunning examples of this. In 1918, before her big algebra papers, she proved a theorem in mathematical physics that is now simply called Noether's theorem. And it says something so profound that physicists are still marveling at it a century later. Here's the idea. For every continuous symmetry of a physical system, there is a corresponding conservation law. If the laws of physics don't change over time, that's a symmetry, the symmetry of time translation, then energy is conserved. If the laws of physics are the same everywhere in space, spatial translation symmetry, then momentum is conserved. If the laws of physics don't depend on which direction you're facing, rotational symmetry, then angular momentum is conserved. Think about what that means. The most fundamental laws of physics, conservation of energy, conservation of momentum, aren't just empirical observations that happen to be true. They're consequences of symmetry. They're algebraic facts. The reason energy is conserved is that the universe has a particular symmetry, and Noether's theorem tells you exactly how to go from the symmetry to the conservation law and back again. Algebra, abstract, structural, group-theoretic algebra, is woven into the fabric of physical reality. And this is where the story starts to get really interesting for the modern world, because once physicists understood that symmetry groups govern the fundamental forces, they started using algebra not just to describe nature, but to predict it. In the 1950s and 1960s, physicists like Murray Gell-Mann and Yuval Ne'eman used group theory, specifically representations of a group called SU3, to organize the zoo of subatomic particles that were being discovered in particle accelerators. Gell-Mann noticed that the known particles fit into patterns that matched the mathematical structure of SU3 representations, and those patterns had gaps. Empty slots where a particle should be but hadn't been observed yet. So he predicted new particles to fill the gaps. And when experimentalists went looking, they found them. The omega- baryon, predicted by Gell-Mann in 1962, was discovered at Brookhaven National Laboratory in 1964. Algebra predicted the existence of a subatomic particle. Let that sink in for a moment. The entire standard model of particle physics, our best current theory of the fundamental forces in particles, is built on symmetry groups. The electromagnetic force corresponds to a group called U1. The weak nuclear force corresponds to SU2. The strong nuclear force corresponds to SU3. The full gauge symmetry of the standard model is the product of all three. SU3 times, SU2 times U1. Every force, every interaction, every particle, described by the algebra of group representations. Noether would have appreciated that, I think. Galois certainly would have been astonished. But algebra's reach into the modern world goes far beyond physics, and this is something that might surprise you. Let's talk about something you probably use today without thinking about it. Encryption. Every time you buy something online, every time you send a message through a secure app, every time your browser shows that little padlock icon, Algebra is working behind the scenes to keep your information safe. And not simple algebra, deep, abstract, structural algebra of exactly the kind we've been discussing. Take one of the most widely used encryption systems, RSA, named after Rivest, Shamir, and Adelman, who published it in 1977. The security of RSA rests on a fact from number theory that's intimately connected to abstract algebra. It's easy to multiply two large prime numbers together, but it's extraordinarily difficult to factor the result back into those primes. We're talking about primes with hundreds of digits. Your computer can multiply them in a fraction of a second. But given only the product, finding the original factors could take all the computers on Earth longer than the age of the universe. That asymmetry, easy one way, hard the other, is what makes the whole system work. And the mathematics that makes RSA tick involves modular arithmetic, which is really group theory in disguise. When you do arithmetic modulo some large number, the numbers form algebraic structures, groups, rings, and the properties of those structures are what guarantee that encryption and decryption work correctly. Euler's theorem, which tells you about the behavior of powers in modular arithmetic, is the engine under the hood. And Euler's theorem is a statement about the structure of a particular group. More recently, cryptographers have turned to elliptic curves. Yes, the same elliptic curves connected to the elliptic functions that Hermite used to solve the quintic. An elliptic curve is a curve defined by a cubic equation, and the remarkable thing is that the points on an elliptic curve form a group. You can add 2 points on the curve and get a third point following a geometric rule, and this addition satisfies all the group axioms. Elliptic curve cryptography exploits the difficulty of a problem called the discrete logarithm problem in these groups, and it achieves the same level of security as RSA, but with much smaller keys, which makes it faster and more efficient. It's used in your phone right now, probably. The algebra of abstract groups, born from Galois' desperate midnight notes about the symmetries of polynomial roots, is literally protecting your bank account. And there's something almost poetic about that connection, if you think about it. A 20-year-old in 1832, scribbling by candlelight because he believed he would die the next morning, working out the deep structural reasons why certain equations can't be solved by radicals, and nearly 2 centuries later, the mathematical framework he invented is the backbone of global digital security. He couldn't possibly have imagined it. Nobody could have. And that's one of the things that makes abstract mathematics so extraordinary. You never know where it's going to end up being essential. But algebra's transformation into an abstract science didn't just give us tools for physics and cryptography. It also changed how mathematicians think about mathematics itself. And one of the most dramatic examples of this is something that happened in the middle of the 20th century, when a group of mostly French mathematicians decided to rewrite all of mathematics from the ground up, starting from the most basic structures they could identify. They called themselves Nicolas Bourbaki, and the name itself is part of the charm of this story, because Nicolas Bourbaki wasn't a real person. It was a pseudonym, a collective pen name adopted by a group of mathematicians who wanted to strip away individual ego and present their work as a unified, authoritative voice. The founding members included André Weil, Henri Cartan, Jean Dieudonné, Claude Chevalet, and several others, and they first came together in the mid-1930s in France, originally with the modest goal of writing a better analysis textbook. But the project grew. It grew enormously. What started as a replacement textbook became an attempt to rebuild the entire edifice of mathematics from scratch, organized not by traditional subjects like geometry and number theory and calculus, but by structures. And when I say structures, I mean exactly the kind of algebraic structures we've been talking about: groups, rings, fields, topological spaces, order relations, treated as the fundamental building blocks out of which all of mathematics could be constructed. The Bourbaki project was deeply influenced by Emmy Noether's philosophy. That idea she championed, that what matters in mathematics is not the specific objects you're studying, but the structures they carry and the maps between them. Bourbaki took that idea and ran with it as far as it could possibly go. Their multi-volume work, called Éléments de mathématiques, and notice the singular mathématique, not the plural mathematiques, because they believed mathematics was one unified thing, not a collection of separate subjects. This work began appearing in 1939 and continued for decades. It was rigorous to an almost intimidating degree. Every concept was built from the ground up, starting from set theory, moving through algebraic structures, topological structures, and then showing how the interplay of these structures generated all the mathematics you could want. Now, here's the thing about Bourbaki. They were controversial, enormously so. Many mathematicians found their approach sterile, overly abstract, drained of intuition and geometric imagination. The criticism was that Bourbaki cared so much about logical architecture that they squeezed the life out of mathematics. There's a famous story, possibly apocryphal, about a Bourbaki seminar where someone drew a diagram on the blackboard and was told to erase it because diagrams weren't rigorous enough. Whether or not that actually happened, it captures the spirit of the criticism. And there's some truth to it. If you pick up a volume of Bourbaki, it can feel like reading a legal document. Definition, theorem, proof, definition, theorem, proof, with very little motivation or intuition along the way. But here's what's also true. Bourbaki's influence on 20th century mathematics was immense. Their insistence on thinking in terms of structures fundamentally shaped how algebra, topology, and analysis were taught and practiced. The language they developed, or standardized, really, became the common language of professional mathematics worldwide. When a mathematician today talks about a morphism between structures, or an exact sequence, or a universal property, they're speaking in a dialect that Bourbaki helped codify. And the idea that mathematics is fundamentally about structures and their relationships, that idea won. Not in Bourbaki's most extreme form, maybe, but the basic philosophy became the water that modern mathematics swims in. And this is where algebra's story connects to something even broader, because once you start thinking about structures and the maps between them, you inevitably start thinking about the maps themselves as objects worth studying. And that leads you to one of the most powerful ideas in all of 20th century mathematics, category theory. This was developed in the 1940s by Samuel Eilenberg and Saunders Mac Lane, and at first it seemed like a minor technical tool, a way to keep track of the relationships between different algebraic structures. But it turned out to be something much deeper. Category theory gives you a language for talking about mathematical structures at an even higher level of abstraction than Bourbaki's approach. Instead of focusing on the internal details of a group or a ring or a topological space, you focus on how these objects relate to each other through structure-preserving maps, functors, natural transformations, adjunctions. It's algebra about algebra. in a sense. It's the study of the patterns that recur across completely different areas of mathematics. Let me give you a taste of why this matters, and I'll try to keep it concrete. Think about the integers, the whole numbers with addition. That's a group. Now think about a vector space. Say, all the arrows you can draw in three-dimensional space with vector addition. That's also a group, a different kind, but still a group. Now, there are maps from one group to another that preserve the group structure. They're called group homomorphisms, and we've talked about those. Category theory says, forget about the internal details of these groups for a moment. Instead, think about the entire collection of all groups and all the homomorphisms between them as a single mathematical object, a category. And then you can ask, what are the patterns in this category? What are the universal constructions? What happens when you compare this category to the category of, say, topological spaces and continuous maps? And here's what's wild. You find the same patterns showing up in both categories. Constructions that look completely different on the surface turn out to be instances of the same abstract categorical phenomenon. Products of groups and products of topological spaces are both examples of the same universal construction. The first isomorphism theorem for groups has an analog for rings and for modules, and the categorical perspective tells you why. It's the same structural pattern manifesting in different settings. This is Noether's philosophy taken to its logical extreme. You're not just studying structures anymore. You're studying the structure of structures. Now, I realize this is getting pretty abstract, and that's okay. You don't need to follow every detail. The point, the thing I want you to carry with you as you drift, is this remarkable trajectory. Algebra started as the most practical thing imaginable. Babylonian scribes figuring out how much grain to store, how to divide an inheritance, how to calculate the area of a field. It was recipes, procedures, do this, then do that, and you'll get your answer. And over the course of about 4,000 years, it transformed into something so abstract that it became a way of thinking about the nature of mathematical truth itself. But, and this is the beautiful part, it never stopped being practical. Every layer of abstraction, no matter how rarefied it seemed at the time, eventually found applications that nobody anticipated. Think about where we've been tonight. The Babylonians' quadratic recipes became al-Khwarizmi's systematic methods, which became the symbolic algebra of Viet and Descartes, which made analytic geometry and calculus possible, which gave us physics and engineering. The Renaissance struggle with cubic and quartic equations forced mathematicians to accept imaginary numbers, which turned out to be essential for quantum mechanics and electrical engineering. Galois' abstract group theory, born from the question of which equations can be solved by radicals, became the language of particle physics and the foundation of modern cryptography. Noether's abstract algebra of rings and ideals gave us conservation laws in physics and error-correcting codes in communication. Category theory, the most abstract layer of all, has found applications in computer science, particularly in the design of programming languages and type systems. The programming language Haskell, for instance, is built around concepts drawn directly from category theory, monads, functors, natural transformations. These aren't metaphors. They're the actual mathematical structures implemented in code. So when someone asks, as people sometimes do, what's the point of abstract algebra? Well, this is the point. The point is that abstraction is how mathematics discovers deep truths that apply across many different domains at once. When you prove something about groups in general, you've proved it simultaneously. about symmetries of crystals, about modular arithmetic, about permutations, about matrix multiplication, about elliptic curves. One proof, infinitely many applications. That's the power of abstraction. That's why algebra evolved the way it did, not because mathematicians wanted to make things harder to understand, but because they kept noticing that the same patterns appeared in different places, and they wanted to understand why. And this brings us to something that's happening right now, in our own time, that connects back to algebra in ways that might surprise you. Because algebra isn't just a historical subject, a story with a beginning, middle, and end. It's a living, evolving field, and some of the most exciting developments in mathematics today are deeply algebraic in nature. One of the most celebrated mathematical achievements of the 21st century so far is the proof of the Poincaré conjecture by Grigori Perelman in 2003. Now, the Poincaré conjecture is a statement about topology, about the shapes of three-dimensional spaces, and Perelman's proof used techniques from differential geometry and analysis, not algebra directly. But the conjecture itself is part of a larger program to classify manifolds, and classification problems are fundamentally algebraic in spirit. You're trying to sort objects into categories based on their structural properties and the invariants you use to tell them apart, fundamental groups, homology groups, cohomology rings, are all algebraic structures. Or consider the Langlands program, which is sometimes called a grand unified theory of mathematics. Robert Langlands proposed it in the late 1960s, and it posits deep, unexpected connections between number theory, algebraic geometry, and representation theory, which is the study of how groups can act on vector spaces. The Langlands program suggests that problems about prime numbers and equations over the integers can be translated into problems about symmetry and group representations, and vice versa. Some of the biggest breakthroughs in number theory over the past few decades, including Andrew Wiles's proof of Fermat's last theorem in 1995, can be understood as establishing special cases of the Langlands conjectures. And Wiles's proof itself is a beautiful example of how algebra connects to everything else. He proved a statement about a simple equation, x to the n plus y to the n equals z to the n, by proving a deep algebraic result about the relationship between elliptic curves and modular forms. Those elliptic curves, again, the ones that form groups, the ones that protect your bank transactions, they're everywhere. And there's something else happening right now that takes algebra into territory that would have been unimaginable even a few decades ago, something that connects the most ancient algebraic ideas to the most futuristic technology currently under development. I'm talking about quantum computing, and the algebra that makes it possible is fundamentally different from anything we've encountered before. Because quantum computing doesn't just use algebra, it lives inside algebra. The basic unit of classical computing, the bit, is either a 0 or a 1. That's it. Two states. You can describe it with ordinary arithmetic. But the basic unit of quantum computing, the qubit, exists in a superposition of 0 and 1 simultaneously, and you describe that superposition using, here it comes, a linear combination of basis vectors in a two-dimensional complex vector space. Every single word in that phrase is algebra. Linear combination. Basis vectors, complex vector space. The state of a single qubit is a vector, and you write it as alpha times the 0 state plus beta times the 1 state, where alpha and beta are complex numbers. numbers with real and imaginary parts, the very same imaginary numbers that Bombelli wrestled with back in the 1570s. And the constraint is that the squared magnitudes of alpha and beta have to add up to 1, because those magnitudes represent probabilities, and probabilities have to sum to 1. So right there, in the most basic building block of quantum computing, you've got complex numbers, vector spaces, and normalization conditions. It's all algebra, and it gets deeper. When you perform an operation on a qubit, when you do a quantum gate, which is the quantum equivalent of a logic gate in a classical computer, what you're really doing is multiplying that state vector by a matrix, a unitary matrix specifically, which means a matrix whose inverse equals its conjugate transpose. That's a condition that preserves the length of the vector, which preserves the probabilities, which keeps the physics consistent. So quantum computation is literally matrix multiplication. It's linear algebra in action, and the specific kind of matrices you're allowed to use, unitary matrices, form a group. They satisfy all 4 of Cayley's axioms: closure, associativity, identity, inverses. The group of all 2x2 unitary matrices with determinant 1 is called SU2. And if that name sounds familiar, it should. It's the same kind of special unitary group that showed up in particle physics, the same family as the SU3 that organized the hadrons into Gell-Mann's eightfold way. The symmetry groups of fundamental physics and the operation groups of quantum computing are the same mathematical objects. That's not a coincidence. It's because both quantum mechanics and quantum computing are built on the same algebraic foundations. Now, when you have 2 qubits instead of 1, something remarkable happens. The state space doesn't just double, it gets much bigger. 2 classical bits give you 4 possible states: 0, 0, 0, 1, 1, 0, 1, 1. 2 qubits also have 4 basis states, but the full state of a 2-qubit system lives in a 4-dimensional complex vector space, and crucially, some states in that space can't be written as simple combinations of individual qubit states. Those are called entangled states, and entanglement is the resource that gives quantum computing its power. The algebra that describes entanglement is the tensor product. You take the vector space of one qubit and tensor it with the vector space of the other qubit to get the combined space. Tensor products are an algebraic construction, developed in the context of abstract algebra and multilinear algebra in the early 20th century, and now they're the mathematical language for describing the most exotic physical phenomenon we know of. Here's what's really wild about this. The reason quantum computers can potentially solve certain problems exponentially faster than classical computers isn't because they try all possibilities at once. That's a popular misconception. It's because the algebra of quantum mechanics allows you to set up interference patterns among computational paths, amplifying the paths that lead to correct answers and canceling out the paths that lead to wrong ones. And the way you engineer those interference patterns is through careful sequences of matrix multiplications, through algebra. The famous quantum algorithms, like Peter Shor's algorithm for factoring large numbers, published in 1994, work precisely by exploiting algebraic structure. Shor's algorithm uses the quantum Fourier transform, which is itself a unitary matrix operation, to find the period of a function, and finding periods is an algebraic problem related to group theory. Once you know the period, you can factor the number using classical number theory. So Shor's algorithm is really a chain of algebraic ideas: group theory, Fourier analysis on finite groups, modular arithmetic, all implemented through linear algebra on complex vector spaces. And the practical implication is staggering. If a large enough quantum computer is ever built, Shor's algorithm could break RSA encryption, the same RSA encryption that depends on the difficulty of factoring large numbers, the same system that protects your online banking. Algebra built the lock, and algebra might pick it. Think about that for a second. The story of algebra, the one we've been tracing all night, has this extraordinary circularity to it. People in ancient Babylon needed to figure out how to divide land and calculate interest, so they developed techniques for solving equations. Those techniques traveled through Greek geometry, Indian arithmetic, Islamic scholarship, Renaissance duels, and Enlightenment abstraction, until they became a vast, interconnected web of structures, groups, rings, fields, vector spaces, categories. Along the way, imaginary numbers went from being embarrassing fictions to the language of quantum mechanics. Finite fields went from being pure mathematical curiosities to the backbone of internet security. And now, in the 21st century, the most advanced technology humanity is trying to build, a computer that exploits the fundamental weirdness of quantum physics, is essentially an algebra machine. It manipulates vectors and matrices in complex vector spaces, using operations that form groups to solve problems about number theory and optimization. The entire arc of algebra, from what number times itself gives me 9 to how do we manipulate entangled qubits, is one continuous story. Each generation built on what came before, often without knowing where it would lead. And that's maybe the most beautiful thing about algebra, the way it keeps surprising us with its usefulness. There's a famous essay by the physicist Eugene Wigner, published in 1960, called The Unreasonable Effectiveness of Mathematics in the Natural Sciences. Wigner marveled at the fact that mathematical structures developed for purely abstract reasons kept turning out to be exactly what physicists needed to describe the real world. Complex numbers, group theory, Hilbert spaces, fiber bundles. Mathematicians created these things because they were internally beautiful and logically compelling, and then physicists discovered that nature was already using them. Wigner called this unreasonable because there's no obvious reason why the universe should be so deeply mathematical. But if you followed the story of algebra from the beginning, you might feel like there's a pattern here. Every time algebraists pushed further into abstraction, every time they said, forget what the symbols mean, let's just study the structure, they ended up creating tools that someone, somewhere, eventually needed. Emmy Noether's abstract ideal theory became the language of particle physics. Galois' group theory became the foundation of crystallography and quantum mechanics. Category theory became the architecture of functional programming languages. It keeps happening, and it's still happening. Right now, algebraists are working on things that don't have obvious applications yet. Homotopy type theory, higher category theory, derived algebraic geometry, and if history is any guide, some of those abstractions will turn out to be exactly what some future engineer or physicist or computer scientist needs to solve a problem that doesn't even exist yet. That's the pattern. Algebra doesn't just describe the world as we find it. It creates a vocabulary for worlds we haven't imagined yet, and then reality catches up. So coming back to where we are tonight, lying here in the dark, thinking about all of this, what is algebra really? At the beginning, hours ago, we said it was about finding unknown quantities. And that's true. It started there. But it became something much larger. It became the study of structure itself, the study of what it means for things to combine, to transform, to relate to each other. It's the science of patterns so general that they show up everywhere, in the symmetry of a snowflake, in the shuffling of a deck of cards, in the vibration of a guitar string, in the encryption of a message, in the spin of an electron. Algebra is the language your GPS uses to triangulate your position, and it's the language a physicist uses to describe why matter has mass. It's the reason your credit card number is safe, and the reason we can predict what happens inside a particle accelerator. It connects a Babylonian scribe scratching on a clay tablet to a researcher in a lab cooling qubits to near absolute zero, and every piece of it was figured out by people. Real, specific, often flawed, sometimes brilliant, sometimes lucky people. A Persian scholar in 9th century Baghdad who wanted to help people settle inheritances. A hot-tempered Italian who broke a solemn oath because he believed the world deserved to know. A young Frenchman who wrote down the most important mathematics of the 19th century the night before he died in a pointless duel. A woman who transformed the entire field despite never holding a proper professorship for most of her career. A collective of French mathematicians who hid behind a fake name and rewrote the foundations of their discipline. Each of them saw a little further than the people who came before, and each of them left behind ideas that outlasted everything else about their lives. That's what I find so comforting about algebra, honestly. It's this enormous, ongoing, deeply human project. Nobody planned it. Nobody sat down 4,000 years ago and said, let's invent a universal language for structure and symmetry. It just grew, one insight at a time, one problem at a time, one curious mind at a time. And it's not finished. It'll never be finished. There will always be another structure to discover, another connection to make, another abstraction that turns out to be exactly what someone needed. And right now, none of that needs to concern you. You don't need to remember any of it. The Babylonians and their quadratics, al-Khwarizmi and his balancing, Cardano and his impossible square roots, Galois and his midnight letters, Noether and her ideals, Bourbaki and their grand architecture. They're all still there, all part of the same long story, and they'll still be there tomorrow. For now, the equations can wait. The variables can stay unknown for a little while longer. The structures and symmetries of the universe are holding everything together just fine without you thinking about them. So let your mind go quiet. Let the numbers and symbols fade into the background, like stars dimming as you drift toward sleep. You've traveled a long way tonight, from ancient Mesopotamia to quantum computers, from scratching in wet clay to manipulating the fabric of reality itself. And all of it, every single piece, started with someone asking the simplest possible question. What's the number I don't know yet? That's all algebra ever was. A way of reaching toward what you don't know, trusting that the structure will guide you there. And that's a good thought to fall asleep to. The idea that not knowing is where everything begins. So rest now. The algebra will keep.